G'day viewers. In this segment we'll talk about ARP and DHCP, two key helper protocols that work with IP. Okay, so the astute viewers among you might have realized that there are a few gaps in my explanation of IP forwarding. In fact, we need a little bit of extra functionality to make things work, and in particular to answer a couple of questions. First of all, nodes need to be able to get an IP address from someplace to use as a source or a destination. And we'll look at how the DHCP protocol does this. Next, even to be able to send a packet across a link, we need to be able to fill in both IP addresses and link layer addresses. And that raises a problem of mapping between the two, going from a destination IP address to what the link layer address is. There's a protocol called ARP, which takes care of this that we'll look at. Both DHCP and ARP are actually pretty good examples of just the real-world kind of glue you would need to make designs work. They're very necessary for IP to work in practice. DHCP provides a little bit of IT support, if you will, whereas ARP provides a bit of glue between all of the layers to join the network layer to the link layer. Okay, so let's look at those questions. The first question here is getting an IP address. So imagine that you're a node, you've just been powered on, you wake up for the first time. You don't know very much. In particular, you'd like to know what your IP address is, what the IP address of the nearby router is, what network you're on, and so forth. One thing you do know that I'll point out now is that you know your Ethernet address. The reason you know this is that the Ethernet address is set on the hardware NIC, on the network interface card itself. So when a node wakes up, if it's attached to Ethernet, it usually knows its Ethernet address, but it doesn't know its IP address. So let's look at how we solve that problem. Well, it could be solved in a couple of different ways. Now, in the good old days, you would simply set up an IP address on a computer by manually configuring it. So someone would fill out a configuration file. Actually, this was really not that long ago, in the 90s. You would do some of this. So you would just add the information by hand. This, you might wonder why this is necessary. For Ethernet, we simply have the address on the NIC so that no one has to encode it later on. For IP, however, the address you have depends on where you are in the network. And that's because, remember, to be able to forward efficiently, we required that all nodes that are sitting on the same network belong to the same prefix. So where you place the computer is going to affect its IP address, so it can't be set at the factory. The second alternative, and the one which of course we're going to follow and use today, it's very popular, is to come up with a protocol for automatically configuring the IP addresses of new nodes as they wake up. This protocol is called DHCP, Dynamic Host Configuration Protocol. And effectively what it's doing is shifting the burden from the user of a system, you and me, to some of the IT folks who help manage the network. If you like, in the manual configuration days, everyone was their own IT for all of their different computers. So let's learn a little about DHCP. I've already told you DHCP, it stands for Dynamic Host Configuration Protocol. It's been around since about 1993. It's now very widely used. Its main function that we're going to look at here is to provide a computer with its IP address. Actually, it doesn't give it to you permanently, it leases you this IP address. So when you wake up, the DHCP server will give you an address and say, you can use this for the next day. The addresses really belong to the network, so the DHCP server can give them out to other nodes over time. Now, DHCP also provides a lot of other parameters too. It's a general configuration parameter for hosts. It's quite useful, not only an IP address, but other things we would need to know to use the network. For instance, you might want to know the IP address of your local router, the network prefix you're on, so you can decide whether you're trying to send to another host on the local network or a remote host, as well as sundry other information that we haven't got to yet, but you could imagine would be very useful, such as a time server to be able to set your clock, and a DNS server, that's to be able to translate host names like www.cs.washington.edu into the IP address. Here's the protocol stack for DHCP. DHCP actually runs as a client-server application between the client that's on your machine when it's woken up and it's trying to talk to the network, and the server, which is running somewhere on the network. It runs on top of UDP, you can see here on the stack, and it uses UDP ports 67 and 68 to identify itself. Actually, if you remember all the way back to the beginning of the course, according to this diagram, DHCP is an application. It's really one of the first applications we're going to look at. It's a little funny because from the network's point of view, it is an application. You could write DHCP using the socket interface and all of that sort of API we looked at, although the one for datagrams, not streams. However, from most people's point of view, DHCP is a protocol hidden in the system. They wouldn't necessarily think of it as something that's an application. So let's see a little more about how DHCP works. There's in fact one crucial issue that it has to solve, and this is the bit in some ways that's most interesting for networks. That's the bootstrap issue. So if your node is trying to contact someone to find its own address because it's just woken up, how does it know the IP address of who it should contact to ask its address? I mean, it's just woken up and it's not configured. If we could configure that, we could probably work out how to configure the IP address. So there is this bootstrap issue of just waking up and getting things done. Now, the answer is, when your computer wakes up, it doesn't know the IP address of the DHCP server that it's trying to talk to on its network. Instead, it uses broadcast communication. It sends a packet on the network that is a broadcast packet. The network will then deliver it to every host on the network. One of those will be the DHCP server. That host will realize that the packet's intended for it, and it will further process it and begin answering DHCP messages. The way you send a broadcast is it uses a special destination address. By convention, the broadcast address is made up here of all ones. So for IPv4, which uses 32-bit addresses, when you write down the all ones and express that in the dotted quad notation here, you see that's going to come out to 255.255.255.255. When we write the all ones in a different format, the format of an Ethernet address that's 48 bits, it looks something like this. The reason is that an Ethernet address is usually written as 6 chunks of 8 bits, and each 8-bit quantity is expressed as 2 hexadecimal digits, where a hexadecimal digit goes from from 0 through F. So F is the highest, it has all of the ones on. When you turn all of the ones on, the broadcast address on an Ethernet is FF, 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 FF. So there you have it. So broadcast is a key component of DHCP. Now that we know what uses broadcast, let's talk about what the exchange is. This is a timeline diagram, so time's going to go down the page as usual here. And we have a line here to represent the client, that's you, a computer that's just woken up, and the other to represent a DHCP server. Now these need to be within one IP hop of one another, so they're on the same network. I see here the same link, the same set of connected links. You could actually have switches in between them, and that would be just fine. So we're really like one IP hop of connectivity that's going across a series of links which are joined by switches, which is logically still one link. How does DHCP work? This is what the exchange looks like. First of all, the client sends a message called a discover. That's basically saying, hello, is there a DHCP server out there? I'd like to contact the DHCP server so I can work out what my IP address is. The DHCP server will then reply with an offer. That offer packet is essentially saying, hello, yes, I'm here, and you could use this address if you would like. If you want to use it, your host will then send a request saying, yes, I would like to take this particular address. And if that's okay, assuming it will be if you're picking the one that's just been offered to you, then the final step is that the DHCP server will send an ACK, an acknowledgement to say, okay, you've got it, now we're both clear on that. The acronym for remembering this is DORA, D-O-R-A. And let me see, yes, okay, I've probably got it right. Here's a cleaned up version of that. And I've noted that the first packet here at least, often more packets in the exchange, the request packet, for instance, so the request packet 2, is broadcast. So it is sent to the IP address and the Ethernet address that's all ones, and so it will be received by this DHCP server, and it will also be received by all other hosts on the network. And they'll simply throw it away because they won't have a DHCP server running on port 68. Okay, so that's the exchange to get an IP address the first time. Once you've got an IP address, the more lightweight operation is simply to renew it. Remember, we said this is a lease, so a DHCP server might give you an address for a day, for 4 hours, for anything like that. Once that time period is up, you're going to want to get another IP address. What you usually want to do is not change your IP address, but keep the same address and say, yes, I'd just like to renew my lease. If that's the case, you can use an abbreviated sequence, just the last 2 packets in this exchange, the request followed by the ACK. The protocol is actually much more interesting if you'd like to look at it in detail. It supports, for instance, replicated DHCP servers, so that an organization can set up several DHCP servers, all of which run in parallel. And using broadcast communication helps us here. That's why the packets are often broadcast, because that way all of the DHCP servers can see what messages the clients are sending and coordinate themselves. But this is a little advanced for where we're at. We're just going to skip over that. I point that out in case you're interested. Okay, we'll move on then to the second problem. The second problem essentially was, how do you send an IP packet? To do that, you need to be able to craft the header, and the header has all sorts of addresses on it. Source and destination IP addresses and source and destination link layer addresses. Now, the question here really, if we're trying to send a packet to a certain IP address, we already have the addresses, is where do we get the link layer addresses to go with the frame to be able to send it over the local link? If we might have an IP address here, and a client might know that it's trying to send a message to a router with a certain IP address, but it still needs to make the packet with all of the addresses, including the link layer, and it might not be sure what link layer address to use. So let me just try and clarify that a little bit by drawing a diagram. So we now have a client trying to send, well, a node trying to send to another node on the same network. To do that, it needs to craft a packet. So here's a picture of the packet. You can see there's the payload at the end, but in front of it we have the IP header, and in front of that we have the link layer header. Those headers have addresses in, and I've just shown the addresses. You have a destination IP address. That's the target. We'll assume that's known because you've got to know somehow, if you want to send a packet to someone, you need to know their address. There's a source IP address. That's your address. Where do you get that? From DHCP. We just answered that question. Now we need to be able to make the link layer addresses on a frame to send something into the network. How do we do that? Well, the source Ethernet address, we can get that. That's on our NIC. Remember, we said these were configured at the factory. So you just sort of ask your NIC what its address is. But we also need this one here, the destination IP address, which is the right destination, the destination Ethernet address, the right address which corresponds to the destination IP address. Where do we get that address? The answer is that we get that address by using the ARP protocol. So let's talk a little bit about ARP. Here's the protocol stack for ARP. ARP stands for, if I didn't say this already, Address Resolution Protocol. So it sits directly on top of a link layer such as Ethernet. There are no servers involved here, so it's actually different than DHCP. Instead, since ARP by definition is going to help us send a frame to a node on the local network, we're going to essentially interrogate everyone on the local network and ask the person who has the right address, who we're trying to talk to just chime up and tell us what their Ethernet address is. So ARP is just going to ask the node with the target IP address to identify itself. Like DHCP, it's going to use broadcast to reach all of the nodes so that its message will go to the target node as well as everyone else. Here's how the exchange works. It's simpler than DHCP. We're still operating on the one logical link here, even if it's a series of physical links connected by a switch. So there's we can't go across routers with this protocol. In this protocol, we simply send a request, And then the request is broadcast across the network. Everyone will get it. The request is going to be looking for the Ethernet address that corresponds to a certain IP address. Whoever has that IP address will get the packet, say, oh, someone wants to know my Ethernet address, look up what their Ethernet address is, and send it back to them in a reply. So here's that cleaned up. And I've also shown you the sort of conventions for what these messages contain. The request usually is viewed as a who is message. It's essentially asking the question, who is or who has IP address 1234? That will go everywhere, including to the node with IP address 1234. That node address will send a reply saying, I do. I'm the one who has that IP address at my particular link address, and it's this thing here. So the node who's asking can then have the mapping between them, and it now knows the destination Ethernet address to use. So it can fill in the frame, send it, and we're happy. We're done with ARP. I'll just make a few comments. Both ARP and DHCP contain elements of discovery protocols. So these are protocols that help nodes find one another. They're very useful actually, and there are more of them. Some of you might have heard of ZeroConf, or if not Bonjour. The Bonjour protocol is Apple's implementation essentially of ZeroConf. These nodes help other nodes find one another for many reasons. Often it's to do with configuration, and so typically in these protocols they use the broadcast trick that we just saw, where a message on a link one logical link will be delivered to everyone on that network. So this is a good way to search for someone. It will get to the party you're intending. And you do this since, with this discovery protocol, you're trying to find a node. If you already knew it, you'd be able to send a message to it directly. But if you're just searching if it's there, nearby printers, for instance, this is how when you open your Mac, it might be able to show you nearby computers to connect to. They're all discovering one another with these protocols. So this is a very handy kind of glue, which is used very much in practice. Okay.